Okay. For those of you who don't know, I'm Matt Anderson. I am somewhere between being a grad student, research tech, and postdoc at CHARA. And over the last few years, we've been beating our heads against the wall trying to get some extragalactic results at CHARA, which we finally do. It's not as flashy as what we've seen today, but it's something. So for this, we've been attempting NGC 4151, prototypical type 1 AGN. We've been thinking about this at CHARA for a very long time. You can see this header from the technical report way back before the groundbreaking for the construction of the array back in 1995 that Brian Mason and Theo were thinking about this long ago. Of course, at CHARA, we only have 1 meter telescopes, and that puts some pretty heavy sensitivity constraints on us. And without adaptive optics, about the best we could do down at K-band is about 8.5 magnitudes. We get almost a full magnitude more with the adaptive optics, and that opens up a couple of options for some things to attempt to observe, including NGC 4151. Of course, most of you will probably know that NGC 4151 has been studied both with the Keck interferometer and the VLTI interferometer long ago. And here you can see an ever-degrading plot from Makoto Kishimoto's paper, who I've been working with from back then, where you can see that even at the 140 meter baselines, we're only getting modest drops in the visibility on this object. So we really need longer baselines, which the CHARA array can offer us. Over the course of my PhD, we've been trying this. In the 4 years, we've been awarded 66 nights, which is quite generous. Many of those nights happen to be during the CHARA meetings. So I would be the only one back in California. I can run the array all myself, and everybody else can come off and go to the pub and have a good time. So it is nice to be at a meeting for once in a long time. I've also, in my time at CHARA, been responsible for deploying the adaptive optics systems on the telescopes. So I've always paired observations with engineering time working on the adaptive optics. I've been working very closely with Makoto Kishimoto at Kyoto University, working on these observations. You can see that in there, that pie plot down at the bottom, that's sort of the breakdown of all of the nights that we've been awarded. NGC 4151 at CHARA is an early season spring object, and weather is just the problem. We're still close to our limiting magnitude, so we need pretty good conditions. And even on top of that, we only have weather conditions. We can open the telescopes this early in the season about half of the time. So that's really hurt trying to do, AGN science at CHARA. On the right there, this is the first good data track of a fringe on NGC 4151. Because we're so close to the sensitivity limit for the classic beam combiner, it's very hard to locate the fringes against the background. So what we came up with is to start our recording. So we've got the fringes coming in on a calibrator and then move the telescopes without restarting the recording to the AGN. And this requires that you need a calibrator very close to your object in order to just drop it in like this. But this is how we found the fringes and have kept track of them in order to record some data. So this was an exciting plot for me anyway. The data reduction that we got, 66 nights came down to 6 nights where we actually were able to record data. 4 nights out of the 6 had good enough data to look into to try and get some information out of. For normal observations, the red fluor reduction pipeline is the standard at CHARA for the classic and the Klein beam combiners. And it works just fine on good signal to noise data, but it gets trickier when the signal to noise comes down toward the detection limit, and it just gets hard to edit your data when you're so, the signal to noise is so low. So Makoto Kishimoto wrote a custom pipeline to reduce this data, looking at the best data sets with the highest signal to noise. The pipelines agree, so the visibility is coming out as good. On the right here, the top, we've just got the noise subtracted mean power spectrum from our data set. And below that, you've got the power spectrum waterfall plot. You can see the fringes all the way through the data recording. A comparison between the IDL pipeline the Makoto wrote and the traditional red fluor I've shown here for a good high signal to noise case. The IDL from Makoto is on top and the regular usual red fluor is on the bottom. On the left two plots in the IDL are the same as the plots below from red fluor. And you can see just the scans, the individual scans on the leftmost and the power spectrum waterfall on the right. And you can see in here pretty strong fringes. And the main point here is that if you're editing data to throw out bad scans with red fluor, you have to work with that one on the lower left. And even on the good data for such a faint object for us, it's very, very difficult to do. If you go to a low signal noise case, it gets much worse. You know, you can kind of convince yourself we have a fringe here. In the power spectrum, it's more obvious, but it's very hard in those left-hand plots to say, I need to edit out these scans or those scans. So in Makoto's pipeline, that's much easier. So you can dump out the data where the alignment suffered or the passing cloud or the AO wasn't working quite right in order to get good data reduction. So out of all of this, we came up with a whopping 6 visibility measurements. We do go out to 250 meters. Our baseline selection was predetermined by where there were deformable mirrors installed and working on telescopes. So it wasn't necessarily what we would have chosen to do, but it's what we ended up with. And it worked pretty good. And you can see here that we've added in some of the old Keck interferometer data just to fill out the UV sampling. It just coincidentally happens to be quite complementary. But we're getting visibilities down to about 0.3. So, you know, we're resolving as we wish and better. So we're happy to have some real measurements here. So with the added in Keck data, we did a thin ring fit. And the main points here, I guess, are that we've got a pretty significant minor to major axis ratio, which you can use to come up with inclination about 45 degrees, which matches the multi-slit modeling that's been done previously. We've also, I'm sorry, I lost myself. The position angle of the axis for the ring is approximately perpendicular to the radio axis. I get somewhat confused here because when I did my modeling, I didn't use the major axis, I did the rotational axis. But it's approximately perpendicular, which is sort of what we'd expect based on what's going on. But we have to be careful because this Keck data we've added in is over a decade old. So really, we'd like to have more data with good UV sampling at multiple baselines in the same kind of epoch where we can be very sure that we're not, you know, glossing over a major change in size. So we will continue observing at present with NGC 4151 because we want to get that UV sampling. We actually had some success in March, and when I go back next week, there's more observing attempts upcoming. The forthcoming Silmaril instrument should give us a few more magnitudes in the best case scenario. If you haven't seen Cyprian's poster on that, take a look. And we're getting better and better with the AO. It's on 5 out of the 6 telescopes. We're getting better at optimizing it and using it. So we're hoping to have, something of an AGN program at CHARA in the future. On the right there, that's just a quick and dirty plot from cross-referencing SIMBAD AGNs brighter than 12th magnitude in K with the 2-mass point source catalog. So we can't guarantee that we can observe all of those without some careful research into that. The point is, the Silmaril is going to bring us more AGNs at CHARA. For more information on the AO talk, the AO system, I'll be talking about that tomorrow. So my main conclusions here are, with our meager data, is that the near infrared emission does seem to be coming perpendicular to the polar axis. And this is consistent both with what we see at larger scales in the visible, as well as the sort of developing paradigm shift coming from the mid-infrared interferometric results. And we're hoping that we're going to be able to do a lot more AGN at CHARA in the future. So thank you. If you've got some questions, I'll do my best.
Okay. Any questions? Can't see them anymore. From Jeremy, please go ahead. We can't hear you if you're speaking.
I think it was on applause.
Oh, sorry, I missed this. Okay, so if there are no questions, I have one.
Okay.
So if you do get this expansion to 12th magnitude, if this large increase in samples, which is something we've also been considering with like Gravity Plus and whatnot, do you have any plans for like a survey, or do you just want to do a few well-detailed objects?
I think it would be best to sort of plan a survey as best we can. It's difficult to do object selection with AGNs because they're extended objects and all of the listed magnitudes are, sort of integrated over space, and it can be a little tricky, but we definitely would like to put together a list of interesting objects and do a survey.
Okay, thank you.
Stefan Kraus, Exeter. Did you try other beam combiners like Merck X or Mystic?
So I've talked to Narcy about it quite extensively. We think NGC 10 or 4151 is too faint for Merck X and Mystic. We have been considering trying it on NGC 1068, which is very likely way over resolved for us. I'm interested to see what happens with the gravity chip install next week. If there's some extra sensitivity there, we might be able to look at a couple of these with multiple telescopes, which, closure phases are nice.
Okay. We have a bit more time if there's any further questions. No? All right, and thank you very much.